The first type of equilibrium calculation is finding the equilibrium constant for an equilibrium reaction. So for this example right here, the reaction reaches equilibrium when the concentrations of different species have the values shown up here. It's in order to calculate the equilibrium constant for this example, you just need to set up the equilibrium constant expression. So the equilibrium constant is going to equal the ratio between the product concentration to the reactant concentration. So it's the concentration of methane times the concentration of water divided by the concentration of carbon monoxide times the concentration of hydrogen to the power 3. And then you plug in the actual concentrations at equilibrium for each of these substances. And remember, this is the number of moles at equilibrium, and this is the volume of the container. So in order to find molarity, it's going to equal moles divided by volume. So you have to divide the two quantities. So which is going to give you for methane is going to be 0.0387. Water is the same quantity, it's 0.0387 molar. And carbon monoxide is going to be 0.0613. Hydrogen is going to be 0.1839 to the power 3, should give you 3.93. This is the equilibrium constant. The second type of calculation is going to be finding equilibrium concentrations for different substances based on the equilibrium constant for a reaction. So for this reaction shown up right here, the equilibrium constant has a value of 56.6. And if you start with 1 molar concentration of each of the reactants, write down an expression for the equilibrium constant, which is again the concentration of the products to the power of the molar coefficient divided by the concentration of the reactants to the power of their molar coefficient. So this is your first step. Second step is set up a strategy of what we call initial change equilibrium. So you start with the initial condition for the reaction, and as we said, you have hydrogen, you have iodine, and you have the product. In the initial condition, you started with 1 molar of hydrogen, 1 molar of iodine, but you have 0 product. You have 100% reactants, 0% product, which doesn't have a ratio that equals the equilibrium constant for the reaction. So what you expect in this case is that the reaction is going to proceed to the right-hand side to make some products. That what makes sense. And in this case, an X amount of hydrogen will get consumed and react with a same amount of iodine because the ratio is 1:1. So whatever amount of hydrogen will react will consume the same amount of iodine, and that is going to produce 2x of the product because the ratio is 1:2 between reactants and products. And that is going to keep going till the system reaches equilibrium, and the concentration at equilibrium is going to be the initial concentration minus the amount that reacted or got consumed. And same thing for iodine, initial concentration minus the decrease. And for the product is going to be the amount that will form during the change. And what you need to do is just substitute for the equilibrium values in the expression for the equilibrium constant right here. So 56.6 is going to equal the concentration of HI at equilibrium, which is going to be 2x raised to the power of 2. And that is divided by the concentration of hydrogen, 1 minus x, times the concentration of iodine, which is 1 minus x. So it's basically 1 minus x squared. So it's going to be 2x to the power 2 divided by 1 minus x squared. And you can simply take the square root of this Square root of this is going to cancel the two powers. The square root of 56.6 is 7.524. Is going to equal 2x divided by 1 minus x. And you can rearrange this. So 1 minus x is going to equal 2x divided by 7.524, or 0.2658x, and rearrange it to solve for x, and it's going to give you x equals 0.79, which means the concentration of hydrogen, which is going to be the same concentration of iodine at equilibrium, is going to be 1 minus x, or 1 minus 0.79, so it equals 0.21. So the concentration of HI is going to be 2 times x, which is going to be 1.58. These are the equilibrium concentrations for different species in the reaction. So in general, whenever you set up an equilibrium calculation, this is the strategy that you use. You need to start by writing the expression for the equilibrium constant. This is going to be your main equation to solve for whatever quantity you want. And think about what is expected to happen. Is the reaction going to proceed to the right-hand side or to the left-hand side? Which species will increase and which species will decrease? And then use the stoichiometry to correlate the change of each substance to the others. So an X amount of a substance will produce an X amount of the product, or 2x amount of the product, based on the molar coefficient of the balanced equation. And you will set up the equilibrium constant expression using the changes that you proposed and solve for the variables that you introduced, and use it to calculate the equilibrium concentrations of different substances. So a second example is this reaction right here. And again, if you start from 1 mole of each of the reactants and 0 of the products, and this is the volume of the container, and this is the equilibrium constant for the reaction. The first step is write down an expression for the equilibrium constant for the reaction. So the equilibrium constant equals the ratio between the concentration of the products, which is the concentration of carbon dioxide times the concentration of hydrogen, divided by the concentration of carbon monoxide times the concentration of water. And the second step is think about what change are you expecting for the reaction. So you start with the initial condition with carbon monoxide of a concentration of 1 mole divided by 50 liters to get the molarity, which is 0.02 molar. And same thing for water, it's a 0.02 molar concentration. And then you have carbon dioxide, 0 concentration, and hydrogen, 0 concentration. So the change that you expect in this case is that since you have 0 products, the reaction will likely proceed to the right-hand side to make more products. So an X amount of carbon monoxide will react with the same number of moles of water to make the same number of moles of carbon dioxide and hydrogen. So at equilibrium, concentration of carbon monoxide is going to be the initial concentration minus the change. For water, it's the same, initial concentration minus the change. And for carbon monoxide, it's whatever got formed, number of moles that got formed, and same thing for hydrogen. Then we will use these values here in the equilibrium expression. So the equilibrium constant 0.58 equals concentration of carbon dioxide is X, or hydrogen is X, for carbon monoxide is 0.02 minus X, and for water is 0.02 minus X. You could possibly use the strategy I used for the previous example by taking the square root of the whole equation to solve for X, or you can use the quadratic equation expression, which is X equals negative B plus or minus square root of B squared minus 4AC divided by 2A. This equation can be reduced to X squared equals 0.58 times 0.02 minus X squared. So it's gonna equal 0.58 X squared minus 0.0232 X plus 2.32 times 10 to negative 4. You just take this to the other side. So 0 is going to equal 0.42 X squared minus 0.0232 X plus 2.32 times 10 to the negative 4. And you just use these A, B, C into the expression, which is going to give you X equals 2 possible roots, 0.0086 and negative 0.06. Obviously, the that root here doesn't make sense at all because of two reasons. Because it's negative, that's one reason. And the second reason is actually the magnitude of the change suggested by this root is 3 times as the initial concentration of the reactants themselves, which doesn't make sense. It's not possible to react something that you don't have. So that's the correct root that you should use, and that's a change that will happen for this reaction, which is going to equal the concentration for the products at equilibrium. So it's the hydrogen concentration at equilibrium is going to be 0.0086.